If you're looking for room, welcome everybody to the Theoretical Astrophysics Colloquium series, where today we are joined by Nick Wogan, who is here for a lectureship. So Nick is here all week, supported by the TAP's new initiative on planetary atmospheres. So we're very grateful to TAP, and it's also excellent that we could have Nick here for an entire week. The Nick schedule has really started to fill up. It's been circulated. Thank you everybody for signing up for slots there. If you're still looking for a time to meet with Nick, especially after you hear about what he has to say today, let me know and we can try to move some things around. Again, I'm the person managing that, so reach out to me if you want to get on the schedule. So Nick got his PhD from University of Washington in 2023, working with David Kettling there, and then shipped off to NASA Ames Research Center, where Nick is currently an MPP fellow. Nick is certainly an up-and-coming leader in planetary atmospheric chemistry, and is also a real expert in open source software development, which is something wonderful and that we're all going to benefit from for the next couple of days, because Nick has a couple of tutorials that he's doing that you can attend, where he's going to show off some of his great atmospheric modeling tools that are all free and available to you online. So with that, I'm going to turn it over to Nick, and I'm also going to circulate the sign-up sheet that if you didn't sign up outside, we need to keep track of names so that we can keep having cookies. So it's important to get your name on this. And so I will start this in the front and I'll work its way back.
Great. Thank you so much, Ty. And I'm really excited to be in Arizona. It's been about 25 years since I've been here, when I was, I think, 5 years old. So it's been a while. So yeah, today I'm going to talk about the photochemistry and climate of foreign atmospheres, implications for the origin of life on early Earth, and understanding exoplanets observed by the James Webb Space Telescope. This work I did with Natasha Batalha, she's my postdoc advisor, and also my PhD advisor, David Kettling, and a bunch of other people, but these are the main ones right here. Okay, this talk has two parts, and the first part is about the photochemistry of impact-generated hydrogen atmospheres favorable for the origin of life on the early Earth, and part two is on interpreting James Webb Space Telescope observations of K218 of an exoplanet, the K218b exoplanet with a photochemical model. So these topics sound very different, but I think you will see by the end that they're basically the same problem from the perspective of atmospheric modeling. So we're going to start with part one, which is on the early Earth and the origin of life and photochemistry. And before we get into the details of my work here, I want to give you some background on origin of life research. So origin of life research is a field with little data and lots of ideas. So there's little data because the origin of life probably began around 4 billion years ago. So little data has been preserved since then. And so with few constraints on people's thinking, they've come up with all sorts of wild ideas. And so if you were to ask people in the origin of life community to fill in this timeline, what happened between Earth's formation and the origin of life, you would get lots of different timelines. And so today I'm going to be talking about one possible working hypothesis of the many that are out there. This hypothesis looks something like this. So first, there were asteroid impacts that led to unique atmospheric chemistry that put the right molecules in ponds of water on our surface, which allowed for the origin of RNA, and then RNA evolved to become the first life. And I'm going to tell you about this working hypothesis, but we're going to do it backwards. So we'll start with the origin of life and work our way backward to the beginning of the Earth. Okay, so first the evolution of RNA, but before that, what is RNA? So RNA is just a molecule. It's made of smaller molecules strung together called nucleotides. Nucleotides have a phosphate and sugar backbone and a nucleobase. There are 4 different nucleobases of RNA shown by the different colors. They're down here. So you can string these nucleotides together in a different order, and that gets you a different RNA. The reason why RNA is interesting in origin of life chemistry is because they can replicate and evolve by a process called base pairing. So let's imagine this RNA is in a pond of water on the early Earth with lots of nucleotides floating around it. There will be a tendency for nucleotides to base pair with the RNA, making a mere copy, and then base pairing can happen again, and that makes a full copy of the original RNA. And every once in a while, there'll be mistakes in this copying process. There'll be mutations. So this imperfect replication, this allows for Darwin's evolution. And the idea is that you could evolve to get more and more complicated RNAs and ultimately form the first cells. And this, of course, is not completely worked out by any means from an experimental perspective. But there have been experiments that show that when you put RNAs in test tubes, with a little bit of help, they can evolve to become more and more complicated. Another reason why RNA is interesting in the origin of life research is because there's fossils made of RNA in our biology today. So here's a very simple cell, a critical function to all cells. They have DNA. Cells have a bunch of ribosomes. The ribosomes, they read the DNA and they make protein. This is fundamental to all life on Earth, this process here. It turns out that at the core of the ribosome is an RNA, and it's very critical to its function. So people view this RNA as a fossil. So perhaps ribosomes were much simpler and maybe just an RNA molecule in the past, and they evolved to their present, more complicated state. So this is another reason why RNA is very interesting in origin of life research. So the story I've told in the last couple slides is that maybe RNA was the first replicator and that it evolved to become the first life. But a problem with this story is that I have not told you where RNA came from on the early Earth. RNA is a complicated molecule, and it wouldn't just be lying around necessarily. So we don't know the answer to this question. We don't know how RNA could have formed on the early Earth. But people have done some incredible work on this topic and got parts of the way there. So people have shown that with hydrogen cyanide, H2S, and UV light, you can make nucleotide precursors. And other similar research has shown that with phosphate, cyanoacetylene, and a few other prebiotic molecules, you can make cytosine and uracil nucleotides. So that's 2 of the 4 nucleotides of RNA. And this is really exciting work, but where would these ingredients come from? Where would the hydrogen cyanide, the H2S, and the UV light come from? Well, the source of some of these things is pretty obvious. H2S could come from volcanoes, the sun makes UV light, but the source of a molecule like hydrogen cyanide isn't very obvious, or cyanoacetylene. It turns out maybe the most likely source would be methane atmospheric chemistry. And we know that methane atmospheric chemistry makes a molecule like hydrogen cyanide because we've seen it occur in Titan's atmosphere. So Titan is a moon of Saturn, it has methane in its atmosphere, and that photochemistry produces these molecules. But where would methane come from on early Earth? Generally speaking, a lot of the literature expects the early Earth, volcanoes on the early Earth to produce more oxidizing gases like CO2 and nitrogen and water vapor. And methane is expected to be a very small component of the gases released from the Earth. So it turns out that maybe the most likely source of a lot of methane would have been really massive asteroid impacts. So here I'm going to explain to you how really massive asteroid impacts could have made a lot. Okay, so a source of, maybe the most likely source of a lot of methane would be these really big asteroid impacts. So how would these big asteroid impacts make methane? Well, imagine the early Earth. So over here we have the Hadean Earth with a CO2 and nitrogen atmosphere. And we can imagine a massive asteroid impact colliding with the Hadean Earth, and it would vaporize the ocean and make a big steamy atmosphere. the iron, the impactor would have iron at its core, just like Earth has iron at its core. And that delivered iron would react with the steam, and it would make a bunch of hydrogen in the atmosphere. And then as the steam cools, hydrogen could equilibrate with carbon to make methane. So after about 1,000 years, the steam would condense to an ocean, and you'd have a hydrogen, CO2, nitrogen, methane atmosphere. So you'd have an atmosphere that contains methane, capable of producing these important prebiotic molecules, like hydrogen cyanide. So that is this working hypothesis for the origin of life in a nutshell. So first, Earth formed, then there were asteroid impacts that produced methane in the atmosphere. And then that atmospheric methane photochemistry made molecules like hydrogen cyanide. And then hydrogen cyanide rained into ponds of water on the surface of Earth, allowing for the formation of RNA. And then RNA evolved to become the first life. So my research focuses on a part of this working hypothesis. So I work on the part involving asteroid impacts in atmospheric chemistry. So specifically, I simulate the atmospheric chemistry after large asteroid impacts, and I quantify the production of prebiotic molecules like hydrogen cyanide and cyanacetylene. So how do I do this? Well, I'm going to briefly tell you my modeling approach. So I model the atmosphere after an impact, and I do that with two different models. The first model is a zero-dimensional chemical climate model, and it has lots of species and lots of chemical reactions, and it tracks the composition and climate of the atmosphere for a couple thousand years while the atmosphere is really hot and steamy. When the steam condenses to an ocean, then I model the atmosphere with a one-dimensional photochemical climate model. And this model reproduces the modern Earth, the methane chemistry on Saturn, and the main Titan cyanide chemistry. So it is validated as it can be for this application. So I want to take a moment and tell you a bit more about these one-dimensional photochemical models, because that's what I'm using for the first part of this talk and for the second part. So just very briefly in words, a one-dimensional photochemical model describes how atmospheric composition is affected by chemical reactions and vertical gas transport. And then there's also a 1D climate model component that simulates atmospheric radiative and convective energy balance. And this is, so Ty mentioned, this is the open source code that I've developed. It's called Photochem. It's available everybody in the planetary science and exoplanet community. And as Ty mentioned, there's a workshop on Photochem in the next couple of days. And I think people have signed up for that, but I'm sure you could just show up if you're interested in this topic as well. Oh yeah, and I developed Photochem, but of course it's not just me. It was built upon an older code that was been developed for the last 30 years. And of course, putting together the model, I got help from a lot of different people in the community, including people at U of A, like Sukrit Ranjan helped me a bunch, and I messaged Ty Robinson a bunch. So they helped a bunch. Okay, so I used Photochem to model the atmosphere after a massive asteroid impact. So here I'm considering a 900-kilometer diameter impactor colliding with Earth. On the x-axis is time after the impact in years, and the bottom plot shows the gases in the atmosphere, and the top plot is the surface temperature of Earth. So before the impact, we have a nitrogen CO2 atmosphere. At time equals 0, there's a 900-kilometer impact, and it makes the atmosphere hot and steamy. And then you can see as the steam cools, methane begins to form. The methane is the black line there. And that's because methane is thermodynamically preferred at cooler temperatures. But there comes a point where the atmosphere is cold enough where the reactions making methane, they stop. So that's why methane kind of plateaus in abundance at the end of the steam atmosphere. So then the steam condenses to an ocean after 3,000 years, but the atmosphere continues to evolve photochemically. So you can see that the methane photochemistry produces hydrogen cyanide and cyanacetylene, which are shown by the blue and green line, dashed lines, reference to the right axis. These molecules are made for about 1 million years until their production is shut off because the hydrogen in the atmosphere, it escapes to space. And once that escapes, just dramatically changes the preferred chemical species in the Earth. So while this hydrogen is around, the atmosphere is pretty hot. So you can see in the top figure there that the atmosphere is at nearly 400 Kelvin. And this is because hydrogen is a really good greenhouse gas. And then once the hydrogen escapes, the planet cools off to a much more normal temperature like Earth today, close to 300 Kelvin-ish. So in the next slide, I'm going to show you a bunch of simulations like this, but we're going to just look at snapshots of these models 10,000 years after the steam has condensed. And we're going to look at these important prebiotic molecules like hydrogen cyanide. So this is a bunch of different sized impacts from 10 to the 20 kilograms to 10 to the 22 kilograms. And you can see that if you have an impact bigger than 10 to the 21 kilograms, all of a sudden you get really big production of molecules like HCN. The reason for this is a little bit complicated, but it has to do with the methane to CO2 ratio in the atmosphere. So when the methane to CO2 ratio in the atmosphere exceeds 0.1, then all of a sudden you prefer much more reducing hydrocarbon species, like a big hydrocarbon haze, and this promotes the production of these prebiotic molecules. So under our nominal model assumptions, it looks like it takes an impactor bigger than 10 to the 21 kilograms or bigger than 800 kilometers in diameter to make a bunch of these prebiotic molecules. But we can be more optimistic and pessimistic about our assumptions. So if we're optimistic, we need, we get a lot more methane. We can get a lot more methane if we include the effects of nickel catalysts. Nickel can help methane production. So then we only need an impactor bigger than about 600 kilometers in diameter to make a bunch of hydrogen cyanide. On the other hand, we can be pessimistic and assume that the iron inefficiently reacts with the steam atmosphere. In that case, we need an impactor bigger than 1,300 kilometers diameter to make a lot of prebiotic molecules. So I want to put these results in this greater working hypothesis for the origin of life. So what these calculations have shown is that asteroid impacts should make methane in the atmosphere on the early Earth. And that methane atmospheric chemistry, it should produce these critical origin of life molecules like hydrogen cyanide and cyanacetylene. But to make the most of these molecules, you need a pretty big impact. So if you're being optimistic, bigger than 600 kilometers diameter, but if you're being pessimistic, bigger than 1,300 kilometers diameter. And these molecules, they would go into ponds, they dissolve in rainwater, rain out of the atmosphere, and go into ponds on the surface of Earth, where they could participate in origin of life chemistry. But our model has also found that when this is all happening, these ponds, they would be very hot. The surface temperature would be greater than 360 Kelvin. And this could be an issue for origin of life chemistry because molecules like RNA, just big organic molecules in general, they like to fall apart when it gets so hot. So this is potentially an issue, or potentially an issue. We're not for sure if it is, but potentially it is. But there is a possible alternative path. So perhaps when these molecules are made, like the hydrogen cyanide could be preserved in salts. And then later Earth would eventually cool down and these molecules could be released to ponds where they could do prebiotic chemistry that leads towards a replicator like RNA. So that's the end of this first project. It was published last year in Planetary Science Journal. But it did leave a couple questions unanswered in this paper. So, for example, given our understanding of Earth's impact history, how likely were these massive asteroid impacts that could have produced molecules favorable for the origin of life? So was it probable that we could have these 600-kilometer impactors, or was that just never going to happen on the early Earth? Also, when did these impacts most likely occur on the early Earth? So if there is any merit to this working hypothesis, and you do need one of these massive asteroid impacts, if you know when they occurred, maybe that does say something about when life began. So I had a paper come out last month in the Astrobiology Journal that tries to answer these questions. And I'm not going to go into depth over it here, but the basic conclusion is that we find that these big impacts are actually very likely on the early Earth. Probably something like a 90% chance of happening. And they most likely occurred in the Hadean eon, so between 4.5 and 4 billion years ago. And all this is based on the impact history that is constrained by the lunar cratering record and the geochemistry of Earth's mantle. So that is the end of part one. Part one considered the photochemistry of early Earth, billions of years ago. But the thing is that exoplanet atmospheres also experience photochemistry, and we can study them using the same modeling techniques. So that takes us to part two, where we're going to be interpreting James Webb Space Telescope observations of the K218b exoplanet with a photochemical model. So first, some background. In the past decade, demographic studies have found that planets between the size of Earth and Neptune are common. So Earth is, of course, 1 Earth radius. Neptune is nearly 4 Earth radii. And it turns out that a very common exoplanet size is 2.5 Earth radii. A very famous exoplanet of this size is K218b. So K218b is 2.6 Earth radii, 8.6 Earth masses, and receives the same amount of sunlight energy as Earth. So we have a radius and mass for the planet. And that gives us a density. That bulk density can be explained by two different models for the planet. It could be a mini Neptune. So it could be a gas giant where there's a lot of hydrogen that goes very deep into the planet. On the other hand, it could be a habitable world. So you could have a thin hydrogen atmosphere over a liquid water ocean, and then beneath that a lot of high pressure ices. And that would also explain the planet's density. These have been called Haitian worlds in the literature because it's a hydrogen atmosphere over an ocean. So hydrogen and ocean, Haitian. But yeah, anyway. So anyway, this degeneracy, it begs the question, like, is K218b a gas-richmini-Neptune, or could it be a habitable world? To understand whether K218b is habitable or not, around a year ago, the James Webb Space Telescope observed its atmosphere using the transit method. So K218b orbits a red dwarf star, a pretty small star, and James Webb took a transmission spectrum between 0.7 and 5.2 microns. And that data was published in Madhusudan et al. 2023. And here is the data. So x-axis is wavelength of light in microns, y-axis is transit depth. And at first glance, this data looks pretty terrible, but there are actually some spectral features telling us about the atmosphere. So there's a bunch of methane features at short wavelengths, and then there's one CO2 feature. And methane is something like 1% concentration, as determined by the spectra. There is also an extremely weak dimethyl sulfide detection. So this is potentially interesting because DMS is a biosignature gas. So but DMS is only produced by life on Earth, and there's very few abiotic mechanisms for producing it. But the thing is that this detection was extremely weak, and we should definitely not believe it at this point. there was also no detected ammonia, H2O, or carbon monoxide. So what does this data mean? Is K218b a mini Neptune, or is it a habitable world? Well, the paper that published that data, Madhusudan et al., they argued that the James Webb data are best explained by a habitable planet. And there are a couple reasons for this, but a main one was because ammonia was not detected, but past theoretical models expected ammonia in the mini Neptune scenario. So I want to take a moment and just state what are they proposing? What is Madhusudan proposing for K218b? Well, it's a thin hydrogen-dominated atmosphere that has methane and CO2 in it with a surface liquid water ocean. In part one of this talk, we considered the early Earth 4 billion years ago after massive asteroid impacts. In this case, there was a thin hydrogen-rich atmosphere with methane and CO2 with a surface liquid water ocean. So from the perspective of atmospheric modeling, these are almost identical problems. And I could very easily use the models that I developed for the early Earth and apply them to K218b. So that's what I did. I applied photochemical and climate models that I originally developed for the early Earth, K218b, to interpret these James Webb observations. And I wanted to answer the question, can a habitable K218b with methane and CO2 be reconciled with our understanding of photochemistry? So I considered a few different cases for K218b. The first was a habitable planet without life. So here I'm imagining an ocean, a thin hydrogen atmosphere, a little bit of CO2 that is consistent with the James Webb data. I put these boundary conditions in the model and simulated the composition of the atmosphere. And this is the result. The main thing, oh yeah, in the x-axis here we have concentration of gas, and on the y-axis is the pressure, so going up in altitude in the atmosphere. And the main thing to take away from this plot is that methane is small. So methane is very small concentration, less than 1 part per billion, because it is photochemically not stable. It is destroyed by photolysis and other oxidizing reactions. So we can simulate the transmission spectrum of this atmosphere and compare it to the data. And it looks like this. So the black line is the model, the dots are the James Webb data, the shading are the effect different molecules have on the spectrum. So this model, it is a terrible fit to the data because there is no methane in this atmosphere, but you need methane to explain a lot of the bumps in the James Webb data. So we can rule out this case for K218b. It is not a habitable planet without life. So then I considered a similar scenario, a habitable K218b with life. So this is a very similar model to the previous one, but now I have included a methane-producing biosphere in the ocean that is pumping the gas into the atmosphere. And it's able to sustain a couple percent methane in the atmosphere against that photochemical destruction. We can simulate this atmosphere's transmission spectrum compared to the data, and this is the result. It produces a much more reasonable fit because you can explain the methane features at shorter wavelengths and also the CO2 feature at longer wavelengths. So apparently this is perhaps, at first glance, an explanation of the data, but you do not need life to explain these observations, as I'll show on the next slide. So the final case I considered was a gas-richmini-Neptune K218b. So this is a giant hydrogen-rich atmosphere that extends very deep into the planet where there's no defined surface really. And so here I'm simulating the atmosphere down to 500 bars pressure, but I imagine the atmosphere goes much deeper into the planet. And so I assumed some reasonable compositions of this hydrogen envelope, and I simulated its photochemistry, and this is the result. Oh, and for this calculation, I needed to estimate the planet's climate, which I actually did with a climate model originally developed by Mark Marley here at U of A. And so I simulated the composition. This is the result. There's some methane in this atmosphere, there's some CO2, and there's also a bit of ammonia. But this ammonia here, it should actually be considered an upper bound, because it turns out that ammonia and nitrogen in general is very soluble in magma. So people imagine that very deep in K218b's atmosphere, if it's a mini Neptune, it would have a magma ocean and gases would dissolve in that magma ocean. And nitrogen is very soluble in magma. And I didn't account for the fact that that nitrogen could be dissolving in the magma ocean. So in reality, we would expect that this would be an upper bound on its concentration. So here is the transmission spectrum of that atmosphere. And it provides a reasonable fit. So you can fit the methane features at short wavelengths. You can do a decent job fitting the CO2 feature. There is a little bit of ammonia absorption, which the original paper claimed was ruled out. So ammonia absorption is shown by the gray at around 3 microns and around 2 microns. Again, this is an upper limit. In reality, we think it should be much lower anyhow. But regardless, even this upper limit is compatible with this noisy data. So we considered 3 cases for K218b. The lifeless habitable planet, it didn't work because methane, it's not photochemically stable in this atmosphere, but James Webb found methane. 2 cases fit the data, the habitable planet with life and the mini Neptune. But these 2 cases are not equivalent in their likelihood. There are some problems with the habitable planet with life case. So the biggest problem is that it's hard to maintain a stable habitable climate on this world. And I want to explain this, but I want to zoom out for a moment and just talk about the runaway greenhouse effect as it pertains to Earth, and we'll make our way back to K218b in just a moment. So quick, I'm sure many of you know about the runaway greenhouse effect, but this is going to be a quick refresher. So the first thing to say about the runaway greenhouse effect is that the water vapor in Earth's atmosphere or an Earth-like atmosphere, in a habitable atmosphere, it depends on the temperature. So here is a model of a habitable planet kind of like Earth with a surface temperature of 280 Kelvin. And you have a little bit of water vapor in our atmosphere, and it's determined by the temperature, right? We have an ocean, water evaporates, it fills the atmosphere until it reaches about its saturation vapor pressure, and then it rains out. So there is a limit to how much water will fill the atmosphere. If by the hand of God I took Earth's temperature and I brought it down to 220 Kelvin, then there'd be a lot less water vapor in the atmosphere because water would reach its saturation vapor pressure more easily. But if Earth was much hotter, then there'd be a lot more water vapor because it wouldn't reach its saturation vapor pressure until higher concentrations. And this effect is very important to the habitability of planets. So in this next slide, I'm going to take a bunch of atmospheres like this, where I varied the surface temperature, and I compute the radiative properties of these atmospheres. So on the x-axis here is surface temperature, and on the y-axis is like a radiative flux at the top of the atmosphere. And the red is the absorbed shortwave radiation. So this is how much sunlight is absorbed. And then the black is the outgoing long-wave radiation. So we have a stable climate at modern Earth where the energy in is balanced by the energy out at 288 Kelvin surface temperature. So the outgoing long-wave radiation, it increases at first at cold temperatures. This is just because hotter things emit more energy. But then it plateaus in how much energy can be emitted. And the reason for this is as the surface temperature gets bigger, you're filling the atmosphere with more water vapor. And water vapor is opaque to this infrared radiation that the planet is trying to emit. And this has huge consequences. So if we were to take Earth and move it to 0.95 AU, so just a bit closer to the sun, then there would be no habitable climate. There would be no place where the absorbed sunlight balances the outgoing long wave in habitable conditions. There still is a climate. So I'm going to change the x-axis out to 2000 Kelvin, and then you can get a stable climate at like 1700 Kelvin. This is because at these really hot temperatures, the surface begins to emit at wavelengths that water is transparent to. So you can find the stable climate. And so this limits how much energy you can get out of a steam atmosphere is the runaway greenhouse limit. It's 290 watts per squared for Earth, and it's like if you were to put Earth at 0.97 AU. So we can take this exact same model and apply it to K218b. So here I'm assuming a 1 bar hydrogen atmosphere and a surface ocean. And you can see that there is no point where the outgoing long wave radiation is balanced by the absorbed short wave radiation. So there is no obvious habitable climate on K218b. And there are a bunch of other models that agree with, these are my calculations, but there are a bunch of others that agree in the literature, at least 4 papers. So it has been proposed that a solution to this is that maybe you could have a really shiny cloud at the top of the atmosphere that reflects away 30% of the starlight. This could lead to a habitable climate, as shown in this plot by the dashed line. You could have a surface temperature of around 320 Kelvin. So maybe this could work, but a problem is that the James Webb spectrum does not show evidence for these high altitude clouds. So a habitable climate is just very unlikely. And this was most recently pointed out by LeConte et al. In 2024, where they actually did some calculations and showed that the observations you cannot have a habitable climate and have it work with the observations. So we'll go back to our summary. The habitable planet with life, it is very unlikely because a stable habitable climate is hard to maintain on this world. So we think that the most likely explanation for K218b is that it's a mini Neptune. And oh yeah, this was published, not 2023, not PSJ, but yeah, it was published this year in AppJ Letters. But of course, the debate will continue about what the nature of this planet is. And I think the way this debate will be resolved ultimately is with more observation. So this table here is showing in green the observations that I showed you by James Webb. And then yellow are observations that have been taken, but not yet published. So these observations are in the hands of the PIs of those projects. So Renyuhu and Niku Madhusudan. And then there are a bunch of observations that will occur in the future as well. So there'll be plenty more data and it will likely hone in on the most likely scenario. So that's it. I just want to summarize. So summary of part 1, we looked at the early Earth, the photochemistry of the early Earth, and in relation to the origin of life. We found that an RNA origin of life might require nitriles, like hydrogen cyanide. Nitriles can be made from methane photochemistry, and methane can possibly be made by massive asteroid impacts. And our one-dimensional photochemical simulation suggests that big impacts, so maybe bigger than 600 or 1,300 kilometers diameter, they produce hazy atmospheres that make these molecules, these important prebiotic molecules, for millions of years. And these prebiotic molecules could perhaps fuel an origin of life. And yeah, this was published in, there's a main article in PSJ, and then there is the related article that I mentioned in astrobiology that is also on this topic. So in part 2, we talked about K218b. James Webb observed K218b and detected methane and CO2, but not ammonia, water vapor, and carbon monoxide. The James Webb data is not compatible with a habitable K218b that has no life because methane is not photochemically stable on this kind of planet. The James Webb data can be reconciled with a habitable planet with a methane-producing biosphere or a mini Neptune with no defined surface. But a stable, habitable climate is very unlikely on K218b. So overall, we prefer the mini Neptune interpretation. And yeah, this was published earlier this year in AppJ Letters. So yeah, that's all I have for you. Thanks very much for listening. I appreciate it.
We certainly have time for questions. If you're joining us online, I'm monitoring the chat room, so you could drop a question into the chat, or we could try unmuting and listening to your question, depending on how the AV goes in this room. But let's start and see if there's any questions in the room. Sure.
Thank you for your talk. I was curious as to how you take into account the impacts in your models. You're talking about kilometer or massive impactors, but I would also, my guess would be that how fast the impact and what kind of energy is released into the impact does count. So I was just curious about how you were taking this into account and what kind of assumptions that you would make to build your models from impacts.
Yeah, so the details are probably important, but we do this, kind of estimate things. So we just like there are, average impactor velocities that we expect, and we assume those. And of course, you have a massive impactor, and you have some amount of kinetic energy, and we don't actually simulate. So there are some people that do smooth particle hydrodynamic simulations, and they simulate where all the pieces go when an impact occurs, and those are very cool. But we don't do that.
Mhm.
We basically say how much energy is there, how much iron is there, and we use that energy to vaporize the ocean, and we use that iron to do chemistry in the atmosphere, and then we simulate the details of that chemistry as the atmosphere evolves. But the details of the impact probably do matter because they will determine where the energy goes and where the iron goes. And there's literature on this that we tried to account for the range of possibilities that these kinds of simulations do suggest. So yeah.
Yeah, of course, you always have to make assumptions.
Yeah.
But thank you.
Yeah.
We have a question online. I want to test to see if this is going to work. So Andrew, I see your hands up if you want to try asking your question.
Yeah, can you hear me?
Barely.
Ty can hear you.
Yeah, essentially, one second.
I try to type, but I'm worried my question might be a little out there and hard to type. I'm basically
No, we got you.
if,
Go ahead.
yeah?
We can hear you. We can hear you
Okay.
well.
I'm basically wondering that if the Earth forms early enough, could it directly accrete molecular hydrogen from the original gas disk, and if that could be relevant? I understand you're getting molecular hydrogen from asteroid impacts, which is perfectly reasonable, but I'm wondering if a very early atmosphere could be relevant as well.
So yeah, it may have occurred, but there was the moon forming impact that occurred sort of after the Earth formed, and right, that likely melted everything down. Anything that you could have done from this perspective of origin of life was certainly erased by the moon forming impact. So that's why we consider it isn't, we're not so worried about what happened before that, and really what happens after that from the perspective of origin of life chemistry.
Okay, yeah, understood. That's just too early and would be erased. All right, thanks.
Questions in the room? Lily?
Yeah, I'm curious. Are you using the canonical definition for like habitable, like what that means in terms of like what we understand it for Earth? And is there any wiggle room there in terms of what habitability could look like on a planet that's not Earth? Significant.
Yeah, so I guess when I say habitable, I mean light on liquid water.
Okay.
And but yeah, I mean, sure, there would be habitable, like even in a lot of these exoplanets, right? There would be technically habitable parts of the atmosphere where life would not be immediately erased if it was in those regions. So I'm thinking about sort of liquid water on the surface. You could have microbes floating around. Yeah.
Sure.
Thanks for the great talk. This might be a naive question since I'm quite out of this field. So in order to produce methane or from molecular hydrogen, or produce these more complex molecules like cyanides from methane, you alluded to several external stimuli like asteroid impacts or UV light, nickel catalysis, and things like that. I'm curious, do energetic particles from cosmic rays or solar flares, do they have a role to play in atmospheric chemistry, and if they could
Yeah.
significantly affect the chemical reactions that go on?
Yeah, they could matter for sure. So yeah, the young sun was much more active than it is today. And yeah, so solar energetic particles back and even now, I don't know so this is not my expertise, but I do know that it is thought that these particles could penetrate pretty deep into the atmosphere and cause chemistry, break apart molecules and sort of start chemistry very deep into the atmosphere. And this could help you produce molecules like hydrogen cyanide for sure. Yeah, you could basically, a challenge in making something like hydrogen cyanide is you need to split apart nitrogen, for example, N2, and that takes, really high energy UV light. Well, if you had solar energetic particles, maybe you could break a bunch of nitrogen apart and you could use those nitrogen atoms to make hydrogen cyanide. And this is something I've only loosely thought about, but there's definitely, it seems like that could matter for sure, but something I didn't consider explicitly.
Devin?
Okay. I noticed that in one of your slides, your model seems to have some sort of initial concentration of N2 and CO2.
Yeah.
I'm wondering how well constrained are those atmospheric abundances, and then how would those impact the generation of hydrogen and later conditions in the model?
Yeah. So I showed you, this simulation after a 800 kilometer, 900 kilometer diameter impactor, and I assumed, I think, a bar of nitrogen, half a bar of CO2, something like that. Yeah, those things are not well constrained on the early Earth. So I'm assuming this on the early Earth. They're not very well constrained. There could be a lot of CO2. There could be up to even 100 bars of CO2. That's like something like the total reservoir of CO2 on Earth is maybe something like that number. And so we did calculations that considered all the range of uncertainty there, and the story that I told holds up. And yeah, you get slightly different production rates. But so there's uncertainty, but it seems like you get the same general picture.
Another question.
Hi, Nick, that was a really fun talk. I learned a lot. Thank you. But so there's a piece that I want to clarify. So between the no life and life, I think that is, you're saying that you're using the same model, but you're adding life in the second one, right? Some sort of spectrum that effectively makes that assumption. And then my question though is, what counts as life? So are we, meaning, I don't mean that in a sort of esoteric way. I mean, are we sort of assuming that plant life? Are we assuming respiration?
Sure.
Or what is it that kind of goes into that model? Or did you play with multiple models? Or
Yeah. So yeah, I say life, but I'm not like a biologist by any means. And when I simulate life, what I mean by that in this model is that I imagine that there are methanogenic life here on Earth, life of all kinds that produce methane. And in this model in the middle here, where I say habitable planet with life, I'm just imagining there is a source of methane from biology. And it could be from any sort of biological mechanism. It's very hard to imagine where that methane, especially on this planet, it's very hard to imagine where that methane can come from abiotic processes. Like you can't really have volcanoes because there's not really rocks, right? The rocks are at the middle of the planet. So yeah, what I mean, there are people here, like Antonin, that do more legitimate models of ecosystems. And I think that would be interesting to try and reconcile with this story. But for here, I'm just imagining some methane production from some life.
Gotcha. So just sort of crank up the knob.
Crank up the methane knob, yeah.
Great talk. Actually, along those lines, have you considered, integrating a sort of crude biosphere model into sort of future modeling attempts of sort of this type of planet, or would that basically require building a whole new package beyond just photochem?
I think it would be possible. So I think, like, I guess, I've seen people, model, they have ecosystem models. I mean, yeah, it would be possible to do that, and I think that would be really interesting to do. So yeah, that seems reasonable and possible. There'd be challenges, but it wouldn't be. Yeah, it could be done. Yeah.
There's a question online from Kayla Smith that's actually related to that. Specifically wondering about kind of timescales in the living planet K218b model. If I could piggyback a little bit on that, I wonder maybe, can you imagine any stabilizing biogeochemical cycles that could help keep a planet like this habitable and inhabited if you have long enough timescales for life to be evolving over?
Yeah. So in terms of like a stable biogeochemical cycle, I think that it would be really interesting if somebody was to actually think through that. Like, you need to balance the atoms, right? Like, if you're putting methane into the atmosphere, that has to be, there's hydrogen and carbon that needs to be coming from somewhere, presumably matter, and where does it, so there is some cycle that would occur that I did not track explicitly, but it would be interesting to consider if there is something that could be pieced together that works. Yeah.
Back to questions.
I'm curious about the 90% thing. So you said that you calculated 90% odds
yeah.
this would happen, right? So this is likely. Was it 90% that this would happen one time in that whole period of the I don't know, I do galaxies, Hadean era,
Yeah.
or is it, and then from that, if it's 90% that it would happen once, what happens if it happens twice in that? Does it totally screw this up and you puff things off completely?
Yeah, so, okay, yeah, it's sure of the details. So yeah, there's this chance that what if you have one of these impacts and, oh, you start life and it's wonderful. And then another impact comes along and it destroys everything or something like that, right? So what we did was we wanted to know the probability of one of these impacts that makes a lot of these important molecules that wasn't then followed by an impact that would vaporize the ocean completely and destroy everything. And that's what that 90% figure is. There's a 90% chance that one of those events would have happened on.
Question in the middle.
Hi, thank you for the nice talk. I'm actually curious about Titan, when you mentioned that it has a methane atmosphere and that your photochemistry model can be validated on it.
Yeah.
Does that mean that Titan 2's methane was also created by some asteroid? And can you track over the next thousands of years what the concentrations of different molecules will look like for it?
Titan, the methane on, there's some mysteries around the methane on Titan. I mean, generally speaking, stuff in the outer solar system has a lot of, methane and ammonia, like cometary material. Like, if you look at, like, I guess, there's people in this room, correct me if I'm wrong, but I generally imagine Titan, being made of comet stuff, like, lots of ices and ammonia and methane and water. And so ultimately the origin of Titan's methane would just be that it formed with lots of methane. And so, yeah, you could simulate Titan's atmosphere. The challenge is that Titan, its methane, there's probably some source of it coming from the planet that is sustaining its concentration in the atmosphere, and there's mysteries around that. So it would be a little bit hard to project into the future. It would be much easier. So what a lot of people do, and what's easier to do, is to sort of simulate the atmosphere today and say, like, okay, there's methane, there's nitrogen. What other stuff would be produced photochemically? That's sort of what we could do. I mean, you could evolve the model into the future, but there'd be a lot of uncertainties, in terms of the methane coming from the surface.
Thanks.
All right, in the back.
So I had another question about the 90% figure. So you said you used for lunar craters to extrapolate. Did you use smaller like impactors to extrapolate to large, like hundreds of kilometers size planetesimals impacting the Earth?
Yeah, where are we here? Back up slide 42. So smaller craters. So on the left. No, so on the left, this is For this calculation, you have to assume some size frequency distribution of objects that are hitting the Earth and the Moon. And this is what we assumed. This is based on the asteroid belt. So this is the size frequency distribution of objects in the asteroid belt. And we did a little extra, you have to do an extrapolation to big impactors, because the biggest thing in the asteroid belt is Ceres, 1,000 kilometers in diameter. But Earth, there's a reasonable chance it experienced that impact. Well, we don't know, but it's possible that the size frequency distribution just keeps on extending. And we varied this and did sensitivity tests and stuff, but so then the asteroid belt with extrapolations is generally what we assumed there. And then the lunar cratering record, that's what's on the right. That's a curve fit to data. This is rocks brought back from the Apollo program.
So does your code make predictions beyond the spectral range of JWST? And if so, where might there be something interesting that another space mission?
Like beyond James Webb? Well, one of the things, one of the things that I've been thinking about, is Habitable Worlds Observatory, just the, trying to simulate atmospheres relevant to that. I know a lot of people here are probably thinking about that topic as well. So, really any telescope that observes any planet is going to be relevant. So observations of Saturn or Jupiter, or observations of or Titan as well. So yeah.
I mean, specifically like a spectral range. Like, is there something
spectral
beyond that?
range.
Yeah.
Oh yeah,
Where would you like to see more data? I guess that's what I'm asking.
oh yeah. Well, let's see. I think to make the model work better, you want ultraviolet observations of stars to get, ultraviolet stellar spectra, which influences the photochemistry in a big time. And I know a lot of people have done a lot of work on this. But it seems like when I pull up their spectra that they give me, there's still all these wonky things in them. And I'm sure it's really well informed and state of the art, but I wonder if there's still, that could probably be helpful. So UV observations, of stars.
Time for one more question.
You talk about one big impactor, but what if we have smaller impactors but much more numbers? Would it work the same?
So the mechanism that I'm imagining and that we're imagining is one that is causing a global change to Earth, within a relatively short period of geologic time, 1,000 years. So if you had, by just luck, two smaller impactors hit the Earth really close to each other within 10 years, then yes, then those two impactors would essentially have the same global effect as one, more or less. But if these impactors are separated by